Let's go. So this is continuity, differentiability, and mod. All right. Let's see. First you got theory, then so theory of all three of these, and then you got exercises. Fine. Right. Let's go for the theory in that case. Yeah, I don't need that. A function is continuous when its graph is okay, it's a single unbroken curve. Yeah, you can say so. And they are saying unbroken, there can be a sudden shift in the slope. That's not breaking, all right? So you might have a curve like this. This is still unbroken. You might have like mod x. This curve, uh, yeah, it's like it's bent. It's not smooth, but it's still continuous. Okay, right. I mean, the formal definition is like, so at some point, your curve will be continuous if the left-hand limit of the function, so as you approach it from the left, and the right-hand limit, those are, I mean, both of them are actually the same as the value of the function, right? When you take the function as kind of like a relation, so going from one set to the other set, so that value of the function, if all three values are in fact the same, then yeah, that's a continuous function. Anyway, so okay, they have different types of discontinuities. First of all, you have a whole discontinuity which is like removable, because you can just define the function at that point to be, yeah, whatever the value is approaching to, right? Then you have what is this, non-continuous, so it's a jump discontinuity. So for example, this whole thing, let's think about this function x minus 1 upon x minus 1. So everywhere other than 1, this is defined and equal to 1. So at x equal to 1, it will have a whole discontinuity because it's not defined there. But you can define it. You can define it. So you can define the function like it's this thing if x is not equal to 1, and it's equal to 1 if x is equal to 1, right? There you go. Now this is a continuous function, right? This is our function f. Call it whatever you want to. That makes sense. So now fx is continuous. So these kind of discontinuities are removable. This is not removable because, like, yeah, the left hand limit and the right hand limits are not same. So, and then there's asymptotic functions. So these are also discontinuous, right? So yeah, clearly the left hand limit and right hand limit are not the same. So you might say, okay, it's like a jump discontinuity, but no, they are actually approaching to infinity, right? So yeah, and that's why it's actually asymptote. It's not a jump discontinuity because it's a special kind of jump, right? You're jumping from infinity to whatever this value. It might be negative infinity, but you're jumping from some really big or really small value to some other value, right? Yeah. And even if like you have a function like this, so mod of 1 upon x, that function is still discontinuous because you have this asymptote over there, right? Okay. Okay. In calculus, the differentiable function is yeah, okay, we know that. The definition is basically like the derivative of the function that is continuous. Then it's a differentiable function, right? At some certain point, of course. Yeah, so like it exists at each point in its domain. The graph of a differential function must have a non-vertical tangent line at every point in its domain. Uh, Wait, okay, that's not the definition that we usually use. So they're saying a differential function is one that has a derivative defined at every point. Okay, so like what about a function like this? So this is actually discontinuous at this point. But then this guy's the left hand limit of our derivative is the same thing as the right hand limit, both being equal to 0. And what about this thing? Is this differentiable or not? I think that depends on how you define it. I want a formal definition. Where is it? So, okay, whatever. Continue a point. Okay, that's what I said. A function is continuous at x equal to a, then it is implied, what? Implies existence of the limit, but not the converse, of course. Right. Okay. Continuity in an interval. Right. Okay. That's pretty mundane. Okay. What's this? Discuss the function. Okay. I don't want that. What about the differentiability thing? Where is it? We want a formal definition, right? properties of continuous functions, we don't care about it. Following important points should be remembered. If f of x is continuous and g of x is continuous at x equal to a, then the product is not necessarily discontinuous at x equal to a. I mean, of course, like just take this function and multiply it by x. So yeah, there you go. Hey, yeah, so something like that. I've seen something like that for the radial probability distribution functions, right? So usually when we just plot phi square versus r, of course, you might get a function like this, okay? Yes, but that is not what you actually want. Like, yeah, okay, this is just phi square. What you actually want is 4 pi r squared phi squared. This would be the total. You get the thing once you do that in physics. Anyway, so like just by multiplying by r squared, now suddenly this function is like this. So yeah, things like these happen. So okay, I should actually probably do it like I know r should not be negative, but then just think of a function. Okay, let's not go into physics and stick to math. Let's take an example. Some function like let's just say 1 upon r. So 1 upon r, it's discontinuous at x equal to, sorry, 1 upon x, and it's discontinuous at x equal to 0, right? But then when you do this 1 upon x thing, so our f of x is just 1 upon x, that times, let's just say x squared, right? So yeah, like f of x is continuous and g of x is discontinuous. Our g is just equal to 1 upon x, and our f is equal to x squared. When you multiply these together, you just get x, and that function is actually defined, right? Yeah. So sorry, that continuous. Yeah, that function just continues, right? Because it just x. So this will be like that. Yeah, and you might say, okay, this function is actually not defined at x equal to 0, so there's still a whole discontinuity. You can say that, sure. Right. But I mean, okay, it's kind of weird actually. Well, whatever. So what kind of function are they talking about? So f of x is equal to x and g of x is equal to sine of 1 upon x. If x equal to, oh, okay, so what they are saying is like, so this whole discontinuity would be if it would be if your function is not defined at this point. I mean, of course, it's not defined. But what if, let's just say, we define g of x to be 1 upon x for all other values of x, and we define it to be 0 for x. Sorry, 0 for x equal to 0, right? So g of x is 1 upon x where x is not equal to 0, and it's equal to 0 where x is equal to 0. If I define a function like this, then of course g is discontinuous at x equal to 0 because left hand limit and right hand limit don't match, right? But f of x times g of x, that is not discontinuous because, right, I mean, like this function is defined everywhere. It's not continuous, but it is defined everywhere. All right. So that times f, that is also defined everywhere, and the value that you will get is it's just it will be x when x is not equal to 0, and it will be 0 when x is equal to 0, right? Yeah. But then you can actually combine these to just say x for all levels of x, because this also fits into this thing, right? Does that make sense? So yeah, there you go. So f of x times g of x, it's continuous even though g is discontinuous, right? So if there's whole discontinuities, those will still be there. But then something like this, that will not carry on to f of x times g of x. Okay, I mean, not necessarily. It might vanish, it might still be there, who knows? Okay, that's awesome. Okay, if f x and g of x are both discontinuous, then the product is not necessarily discontinuous at x equal to a. So they give us an example. So f of x is negative, g of x is equal to, okay, fine. The product is not. Oh yeah, okay, that makes sense. Sure. Okay. Discontinuity. This discussion of discontinuity of function okay, at point x equal to a is meaningful only if the graph of y equal to x exists in the neighborhood of x equal to a. So what you mean is like if the domain ends suddenly at some certain point. So for example, the sine inverse function or something like that, right? Okay, yeah, sine inverse function, right? Oh, so they have something. That's tan x though, not exactly what I. Okay. So for sin inverse x, you know it's only till negative 1 and 1. Only in between this, only in this interval is the function you can find. So can we talk about continuity at this point exactly? Maybe not, because yeah, it doesn't make any sense. It's not defined in this area. So how do you even describe continuity? What does it even mean in the first place, right? Differentiability, I don't know. If continuity is so problematic, what about differentiability? That would be much difficult, right? Okay. At least now we know what continuity is for points that are inside the interval and not on the edge of the interval. Anyway, yeah, whatever. We don't care about that. Okay. Uh, Wait, did I switch off the net? Okay. The graph of f is equal to 1 upon whatever this thing is doesn't exist in 0 to 1. We don't care about that. We just give me differentiability, the definition that you are using. Okay. Isolated point discriminating. Oh, so like this. Huh. So why is this removable? Okay, so you're like changing the value at that point, right? Aren't you actually changing the function itself when you are doing this? I mean, this is like you're just extending the function, but over here you're actually changing the function, right? So is this even removable in the first place? Aren't you actually changing the function? Because yeah, you're altering the definition. That's not good. Okay, they are using it as a removable discontinuity. So I'm gonna do the same. Okay, a removable discontinuity. Oh yeah, I'm gonna know that. Okay, I know it. Just give me the definition of differentiability and then we are good to go, right? Intermediate values, I don't care about that. Wait, okay, let's still read that because who knows, might come in handy. A function is continuous in A to B. Okay, a function like that, which is continuous in A to B, possesses the following properties. If f x, okay, if f of A and f of B possess opposite signs, then there exists at least one. Okay, yeah, we know that. Come on, okay, okay. The first thing is just the extent. It's just a special case of the second one. So, the function y whatever. Suppose fx continues in 0 to 1. Okay, that's just an illustration. We don't want that. We want. Oh, wait, they didn't even tell us what differentiability is. Ah, these people. Seriously. Well, let's do it. In chapter exercise 1, right? Okay. First question. A function is defined as this thing. So it's like x minus theta x plus 2, right? So this upon that is x plus 2 when x is not equal to 3 and it's equal to 5 when x is equal to 3. When x equal to 3, yeah, if you put that in there, it will just be 3. I mean, okay, it's approaching 5 from both sides because x plus 2 when x equal to 3 just becomes 5. Although this doesn't become anything, it just becomes not defined, but its limit is 5, right? And it's actually equal to 5, so it's continuous. It's continuous everywhere, in fact. So yeah, B is correct. Next question. If x is equal to, okay, it's just x plus 1 and then 2 and x equal to, come on, it's the same question as the last time except with different numbers and functions. Okay, yes, it's continuous at x equal to 1. What's the big deal about it? Huh, that was very easy. Okay, function this thing e power 1 upon x is x not equal to 0 and it's 1 if x is equal to 0. When x equal to 0, like it's just e power plus minus infinity, right? So as x approaching 0, then it's just e power plus or minus infinity, and then that's just oh, okay, that's problematic. So when x approaches 0 plus, this is e power infinity, which is actually infinite. And when it approaches negative 0, so 0 minus, then this is e power negative infinity, which is 0. So that means it's yeah, it's like discontinuous, right? So yes, it's discontinuous at x equal to 0. A. Next, fourth. So it's 1 minus cosine x upon x square when x is not equal to 0. All right, it's well defined everywhere, and then it just means it's continuous. Yeah, because these are continuous functions. Sure. Divide by x square. Yeah, okay, I know that. Uh, it's 1 when x is equal to 0. Well, this thing is like 2 sine square of x upon 2 upon x square. So when x approaches 0, it should be square, sorry. When x approaches 0, this thing just becomes approximately 2 times x square upon 4 upon x square. So that just cancels. It's 1 upon 2. It should approach 1 upon 2 from both sides, but then it's 1, so it's discontinuous. Yeah, it's discontinuous at x equal to 0. That makes sense. Fifth, 8. Maybe yes. Next question. Sixth. Oh, okay, that's fourth. Wait, where's fourth? Oh, this must have been fourth, but it's fifth. Fine. Let's do fifth now. Okay, which of the following is continuous at x equal to 0? This function. So, mod of x is going to 1 upon x approaches 0. Yeah, it's going to approach 0. So, that is in fact continuous, right? Well, yeah. Doesn't matter what this is approaching, it's just finite. And that times of 0, 0. Yes. So, yes, this is usually continuous. A is good. What about B? That's 1 as x tends to 0. And, oh, so as x approaches 0 minus, it's, so yeah, okay, just 1. And when it approaches 0 plus, it's just 2. That's a problematic thing. It's discontinuous. So B is not the answer. C, floor of sine x. What? So x less than or equal to 0. Well, it's going to be negative 1, right? Yeah, it's negative 1 when x is less than 0, exactly less than 0, right? When x is equal to 0, yes, that should be the thing, right? When x is less than 0, it's just equal to negative 1. It's lower function, yes. Except, okay, except at, like, at x equal to negative pi upon 2, it's going to be 1 or, oh, okay, yes. I can see what's going on. Oh, no. In fact, that's not a problem. Because, wait, might be a problem. Right. It's not just discontinuous at x equal to 0. It's at a lot of different points that it's discontinuous. But anyway, we only care about at x equal to 0. So yeah, this function in itself, like it's when it's 0 minus, this thing is negative 1. And when it's 0, suddenly it's going to what? 0. So it's discontinuous already. We don't have to look for this thing at all. So C, it's discontinuous. And what about, okay, why am I doing this? Isn't this just single correct, or is this multiple correct? I don't know. Log x minus 1 upon log of 1 plus 2x as x tends to 0. What does this approach? Seriously, just use the Taylor expansion. So e power x minus 1, Taylor expand that, and then approximate, which is approximately x as x tends to 0 upon this thing. Once again, just approximate. So like, okay, what is, so 1 upon 1 plus x is just equal to 1 minus x square, x plus x square and all that stuff, right? So integrate that natural log of 1 plus x is equal to some kind of constant, but we know that constant is just going to be 0 in any case. It just x minus x square upon 2 and so on. So just put 2x in there, right? It's approximately 2x, I would say. So this is just 2x. Yeah, that makes sense. So this should be 1 upon 2, right? That's what this should approach to as x approaches 0, but it's actually 7, so it's discontinuous. Next question, sixth. And of course, this whole booklet assumes that you are good in limits, right? So I won't I won't tell you how I figured out what it's approaching, right? Because you already know that, right? Okay, sixth. So the following functions is continuous at x equal to 1. So when x is not equal to 1, it's this thing. When x equal to 0, it's just wait, we don't care about 0, do we? We just care about x equal to 1, right? Okay, okay. So this thing is like 1 plus x square all the way till x power n minus 1. So when x is approaching 1 from either side, this is just equal to what? Oh, wait, it's not defined in the first place. So it's like a whole discontinuity because it's not defined at x equal to 1, right? And what's this n minus 1 when x equal to... Hey, where's the definition for x equal to 1? You didn't do that. Uh-oh. That's not good. That's definitely not good. It's like n of these guys. Sure. Wait, that doesn't make any sense. We don't care about x equal to 0, we just care about x equal to 1, and they didn't give us anything. So yeah, it's just the whole discontinuity over there because they didn't define it for x equal to 1. So let's move on. Next question. Oh, okay. So A is not continuous. B, mod of x minus 1. Okay, it's like mod of x minus 1 times mod of x plus 1. That's like signum of x minus 1 times x plus 1. X plus 1 approaches 2, but in signum of x minus 1, that approaches 1 or negative. Okay, yeah. It's discontinuous already because left hand limit, right hand limit don't match. So B is discontinuous. What about this guy? So it's x if it's between, okay, let's graph it out. Wait, we don't care about, we just want a point. We don't want the whole function. So at x equal to is, okay, it approaches 1 from the left hand side, then it's just 1. Exactly at 1, it's 1. From the right hand side, so just put x equal to 1 in there, cosine of pi. Oh, uh-oh. That's not good. Cosine of pi. Yeah, that's negative 1. So it's not continuous. Okay, it's just D. Seventh is for what value of k is this function continuous at x equal to 1? It is x plus 1 when it's not equal to 1, right? So yeah, k equal to 2. That's so easy. Okay, 8. From what value of k, the function is continuous at x equal to 1. Come on. It's just a repetition of same kind of things. X minus 1, x plus 2, then x minus 2. Okay, x minus 1 times x minus 2, and that upon x minus 1 is x minus 2. So put x equal to 1 in there, it's just negative 1, right? For what value of k is this function continuous at x equal to 0? X equal to 0, you're saying. Approximate, just 5x upon 3x is just 5 upon 3, right? That's what it approaches as x approaches 0. So 5 upon 3 is the value. What is this? Why are they doing something like, okay, whatever. I mean, it's just the most basic kind of questions, right? Maybe that's why they're doing something like that. Okay. For what value of a, the function is continuous at x equal to 2. Okay. And x equal to 2, this thing is just 1. So this should also be equal to 1, right? So like 2a plus 5 is, what am I doing? That's just equal to 1, right? I guess. So 2a equal to negative 4, a equal to negative 2. Easy as that. Next question. 11th. For what value of k, the function is continuous at x equal to 0. Oh, okay, there's a mod x in there. That's not good. So 2x squared doesn't really matter because it's, yeah, uh, in comparison to this thing, it's not there. Okay, maybe I should write it in a better way. It's like this thing, mod x upon x, and then plus 2x. So basically, it's like this thing, 1 upon 2x plus signum of x, right? Yeah, so when x approaches 0, it's this thing. So, I mean, this approaches 0 in any case. And this is approaching 1 from one side and negative 1 from the other side. So, this is not defined, right? Oh, sorry, it's not continuous, right? That's what I'm saying. So, there's no value of k, so that this would be continuous. 11th, D. Because there's a jump discontinuity. Yeah. 12th. Uh, for what value of k, f of x is continuous at x equal to pi upon 2. So it's 3, and this should also approach 3, I assume. So just put x is equal to pi upon 2 plus h, right? Or maybe something like, okay, I mean, okay, it's like 2x is there, isn't it? Whatever, just do it. K cosine of pi upon 2 plus h, that's like k, and then you got negative and sine of h, and then that upon pi minus 2x, which is just negative 2h, right? This is the thing. So it's k sine of h upon 2h, which is approximately k upon 2, right? So as h approaches 0, it becomes k upon 2. So k upon 2 should be equal to 3. And yeah, it's from the it's from both sides that this happens. So k upon 2 is equal to 3. K should be 6. Next question. 13th is fx is this thing, okay, and this is continuous at x equal to 0, then f of 0 must be, okay, just figure out the limit. These questions, seriously. So it's next. What is this? Log of 1 plus x upon a minus. Yeah, just Taylor expand, right? That's the easiest thing to do. I want something better, and something not like this. I think so. Like as x approaches zero, what limit are we actually dealing with? We are dealing with this limit. Limit as so I'll just say x is equal to a b times h, if that makes sense. So like h approaches zero. Now x, we'll just put that as a b h. Okay, this will be natural log of 1 plus bh in that case, and then you got minus natural log of 1 plus ah, right? Yeah. This is like the limit as h tends to 0. Wow, it's getting very complicated actually. Um, yeah, I mean, I can already see it's kind of a derivative, but then how do I prove that it's a thing? Do I even have to prove it? No. I mean, you guys already know it's a derivative, right? Yeah, I mean, this whole thing, oh God. You could always just approximate this thing as BH and this thing as AH, and then yeah, A minus B upon AB. That makes sense, right? But then let's do it the other way. So A minus B upon AB, and then you got this natural log of 1 plus BH minus natural log of 1 plus AH upon what's this thing? BH minus AH, right? So this thing, as you can see, is just a derivative at x equal to 1, right? It should be, although it doesn't look like that. It's kind of a weird thing going on. But whatever, we don't really care, do we? I mean, we could always do this thing that, okay, no, don't do anything like that. This is good enough. This is the derivative, you can see that. So this is just the derivative at x equal to 1. So the derivative of natural log of x is just 1 upon x, and x equal to 1 is going to be 1. So yeah, a minus b upon ab. That's the limit. Uh, yeah, sure. So that's going to be, wait, is this a minus b or what? No, it should be b minus a, right? Let's look at that. B minus A. That makes sense. So yeah, it just be minus A upon AB, which is A. You could have done this much more efficiently by just approximating. Like this thing, it's approximately X upon A. This thing is approximately. Why is that a oh God, that's a negative. You know what? They just replace. Okay, okay. I mean, I did completely different than what they are doing. Oof. It should have been negative AH over there, right? Yeah. Uh, yeah, then this would be negative of that. Right, okay, I get what's going on. But you know what? I won't do it again using the same kind of thing, using like the derivative definition. No, this approximate. So it's this thing, x upon a minus minus is plus, like plus x upon b upon, yeah, upon x. That makes sense? I guess it should, right? I mean, like negative 1 upon 1 minus x is equal to, okay, sorry, negative natural log of minus x, that's equal to what? X plus x squared plus x. Yeah, you get the thing, right? Of course. Uh, yeah, so approximate this complete thing, negative natural log of 1 minus x, that as x, right? So this is x upon b. That makes sense? Okay. So this is the thing. So of course 1 upon a plus 1 upon b is the limit, which is a plus b upon ab. That's C. Next question. So it's just for this exercise that I'm explaining all of this, right? Next exercise, I won't do it. Okay, 14th. 14th is f(x) is equal to 2 power x plus 2 minus 16 upon 4 power x minus. Okay, interesting. If x, wait, you know what? Okay, let's do it like this. 4, then you got 2 power x minus 4, right? That's the numerator. And the denominator is 2 power x minus 4 times 2 power x plus 4, right? So this cancels just 4 upon 2 power x plus 4 in the limit at least, right? So if x is not equal to 2, you can write it like this thing. If it's equal to 2, then f of 2 is what? So that it's continuous. Okay, as x approaches 2, this thing just approaches what? 4 upon 2 power 2, I guess. Okay, yeah. Yeah, which is just 4 plus 4. Yeah, that should be the thing. 1 upon 2. So it should be D. Next question. Did I mess up somewhere? No, no, I didn't. Next, 15th. 15th is, come on. If f(x) is equal to this thing, it's continuous and x equal to 0, then k is. Okay. So this is like cosine of 2x minus 1 upon, oh, come on, I just don't like this. This is a negative sine square. Okay, fine, just negative 2 sine square of x upon, well, just rationalize this thing. This just becomes what? X square, and then you put that on the top, x square of x square plus 1, uh, plus 1, right? Yeah. So when x is not equal to 0, you can actually do this thing, right? Yeah. So if it's continuous at x equal to 0, what should k be? X equal to 0, this thing approaches 2, and x approaches 0. This whole thing, just 1, is just negative 4. So k should be negative 4. Next question. 16th. 16th is if the function, this function, is okay. So what about, oh, okay, fine. So 1 minus cosine of 7, then you got x minus pi upon 5 times of x minus pi squared. Seriously. So it's like 2 sine squared of 7 upon 2 times whatever this thing is. Call this thing h. H. This thing, oh, wait, not this thing squared, just, yeah, upon 5h squared, right? And this thing just approaches what? 2 times of 49 upon 4, of course. So like 49 upon, oh, there's also this 5. Yeah, okay. So it's not this thing, it's this 2 times 49 upon 4 h squared, that cancels, right? Upon 5. This is just 49 upon 10. That's what this approaches, right? From both sides, in fact. Yes, so this has a removable discontinuity at x equal to pi. That's the thing, right? Jump discontinuity x equal to pi. Okay, not really. Okay, fine, it's just B. Next question. 17th. Okay. The function f(x) is equal to sine x upon x plus 1. Sorry, and x plus 1. Okay. So if it's x, if x is negative, then it's this thing. And if x is positive or equal to 0, it's this thing. Okay. It's continuous everywhere. I mean, when x is not 0, this does look defined everywhere, and then it's like continuous upon continuous, so it's continuous. Yes. And yeah, that should be the thing. Okay. And x plus 1. We know this approaches 1 as x approaches 0 minus, and then this is already 1 at x equal to 0. So yeah, it's continuous everywhere. What's the big deal? Where can it be discontinuous? I don't get it. At infinite number of, why would that be the case? I don't get it. Why is this going to be discontinuous at infinite number of points? I don't get it. It's just x over here. I mean, the denominator is like always defined. Neither are you like going to some kind of asymptote. That's not happening. So why would it be discontinuous? Next question. Consider the following functions. X cubed minus x squared plus 2x minus 2. And this, okay. And this, what about this? Which of the following has a single remembered discontinuity? This is continuous everywhere because it's polynomial. This thing is, so it's like x power 4 minus 2 power 4. So yeah, okay, it has a removable discontinuity. Cool. Because otherwise, if x is not equal to 2, it's just a polynomial actually. So 2 is already there. Okay. Third, x power 4 plus x cubed plus, what is this? Okay, this approaches x, right? As x approaches 0. And oh, okay, so this is actually approaching 0. That makes sense. As x approaches 0, this thing approaches 0. And the inverse of x is like a continuous function defined everywhere throughout the real line. Yeah, yeah, that's right. So this is actually going to be a continuous function. That makes sense. Except x equal to 0 because at that point it's not defined. So it has a removable discontinuity. Okay, so second is there, third is there. What about fourth? Mod of x minus 2 if x is bigger than 1. I mean, I'm recording with sound, right? Yeah, it seems so. Okay, mod of x minus 2 if x is bigger than 1, and this thing if x is less than 1. So it's well defined whenever, yeah, I mean, okay, yeah, it is in fact well defined. What about it? And it's continuous as well at even at x equal to 2. What's the big deal? So at x equal to 1, this, like, it would approach just 1, and this, what will this approach? So it's 1 upon 4 minus 3 upon 2 plus 13 upon 4. It's like 14 upon 4, just 7 upon 2. 7 upon 2 minus 3 upon 2 is 4 upon just 2. So it's approaching 2, huh? What? Why is that the case? Right? It's like 7 upon 2 minus 3 upon 2. That is just 2. It's approaching 2, and this is approaching what? 1. So no, there's it's not having a removable discontinuity. This has, and this has one. So second and third, not fourth. Come on, please don't. What is this? All four? That's not good. You have like a single removable discontinuity, right? That's what you want. I mean, sure, it has. It doesn't even have a single. So one is not there. This is wrong. This is wrong. Okay, both have 4. Why is this having a removable discontinuity? At x equal to 1, this approaches what? This is like 1 upon 4 plus 13 upon 4 is 14 upon 4, which is 7 upon 2, and minus 3 upon 2, which is like 4 upon 2. So 4 upon 2 is just 2. It's not what this approaches. It approaches 1. How does this make any sense? It's not. What? Okay, so it's discontinuous at that point. It has a non-removable discontinuity. Maybe at some other point it is discontinuous as well, and then it's no, but it's not discontinuous in any other place because yeah, that doesn't make any sense. This is defined everywhere. It's defined everywhere. X equal to 0. No, all options are just wrong. It should be second and third, right? So 18th, all are wrong. It's second and third. 19th. If the functions, so I'm sorry, if the function fx equal to this thing is continuous on 0 to infinity, then the number of ordered pairs a comma b is. So basically, where is this continuous, right? Wait, what? Sorry. Okay, if it continues throughout 0 to infinity, then what should a and b be? Oh, that's the thing. Okay, and the number of ordered pairs. Okay, fine. So first you got x squared upon a, then you got a. So it's from 0 to 1. I mean, that's good. It's defined that range. Add x equal to 1 just approaches just 1 upon a, and add x equal to 1, this is actually equal to a. Okay, that should happen. Okay. So what does that mean? A squared equal to 1. That's our first equation. And then what else do you have? So add x equal to square root of 2. This is just equal to a, right? It's approaching a. And at x equal to square root of 2 exactly, it's this thing, right? Which is e square minus 2b, it seems. Huh, that's weird. I mean, okay, number of different ways you can do this actually. Fine, so this is b minus 1 squared minus 1, so just put a plus 1 over there, right? So you could have a equal to 1, right? So a equal to 1, then b would have two values because square root of 2 plus 1 or negative square root of 2 and plus 1, right? So you already got 2, and then if a is equal to negative 1, b will only have a single value. So there's another one. So like 3 ordered pairs. So D should be the option. Next question, 20. 20 is the function f is defined like this. If f is continuous on 0 to 8, then a comma b is. So throughout this interval, huh? Okay. X squared plus ax plus b, if this is like Okay, okay, I get it. Why are they asking us these kind of things? Fine, just put 2 there, then put 4 there, because these are just polynomials, right? We don't have to worry about taking a limit. So, 4 plus 2a plus b is equal to, what's this thing? You put 2, it's just 6 plus 2, it's just 8, right? Yeah. Okay, which means 2a plus b is equal to 4. That's our first equation. Then the next one is when you put x equal to 4 in there. Okay, so you're gonna get like 8a plus 20. Sorry. Yeah, okay, wait. No, that's just b over there. It doesn't have an x over there. Okay, this should be the thing, right? 8a plus 5b is equal to, when you put 4, it's just 12 plus 2, which is 14. That's the other equation. Now you will have to use this. I don't like this. Okay, multiply by 4, just 8a plus 4b is equal to 16. Then subtract a is equal to 82, which means 2a is equal to 6. So a equal to 3. So yeah, a comma b is 3 comma negative 2, which is a option. Next, just check all of these. So first b, second b, third it should be c, fourth a, fifth a, sixth d, seventh b, that's also b, 9th c, a, d, b, c, 14th d, then this is c, then 16th b, 17th a, 18th b, okay, 19th d, and 20a. So 18 should be b, uh, which is 2, 3, and 4. These have removable discontinuities. A single removable discontinuity. What about this guy? It doesn't. Yeah, this doesn't make any sense. N x equal to 1, it's just 1. I mean, this is 1, right? And over here, it's 2, right? Where am I going wrong? Am I going wrong? No, no, I'm not. It has to be like this. Mod of negative 1 is just 1. And so at 1, it's discontinuous and it's not removable. Before 1, it's defined everywhere. Sorry, it's continuous everywhere. And after 1, it's also continuous. So where is our single removable discontinuity in this function? I don't see any. So this is just wrong. Like, no, this cannot be the thing. Okay, let's go to third. So this should have been C, it seems. Okay. I said it's discontinuous at x equal to 0, and they are saying it's continuous. What? How do you do that? Look. If x is positive, this thing. Okay. Let's do it the proper way. If x approaches 0 plus, then yeah, like this thing is going to be e power infinity, which is infinity. When x approaches 0 minus, this thing is e power negative infinity, which is 0, because it's like 1 upon e power infinity. It's like 1 upon 0, which is 0, right? So the left hand limit and right hand limit are not the same. Moreover, it has an asymptote at that point. How can you say that it is continuous? Right, this is just wrong. Okay, so that's it. That's this exercise. Let's go to the next one. Fine. Differentiability. Now we'll get the proper definition. So at a point, the right hand derivative. Okay. Equal to a finite value k, and it's just fine. It is a dash of. All right, that's weird. So you don't have an actual defined value at that point, of course, because they don't define the derivative for you. They only give you the function. So The only condition is that the right hand limit should be the same thing as the left hand limit for the derivative. Yeah, that makes sense. Sure. And of course, like this should only happen if your function is continuous at that point, right? So if it's having a whole discontinuity, it doesn't make any sense because like how do you do this? What even is uh so okay okay, what is this h approaches 0 plus f dash of at x equal to a, right? So if your f of a is not defined, how do you even calculate this limit, right? So yeah, wherever there's a whole discontinuity, you don't have differentiability. Where there's a jump discontinuity, there might be a limit. Okay, no, there can't, because look, if there's a jump discontinuity, um, one of these values must be f of a, right? Okay, or maybe there's no f of a, but then that's once again what I said earlier holds that you can't actually define these things. And if there's a jump discontinuity, then one of these values must be f of a, but that would mean like the slope of this line, which is actually just infinity, that would be either the right hand derivative or the left hand derivative, which would mean that there's no way that, yeah, okay, this doesn't make any sense, right? Yeah. So even though your left hand limit and right hand limit for the derivative might be the same, you don't actually have differentiability anymore because look at this, just look at this, right? Yeah, you can't have it because this is like going to infinity. How can you even do that, right? Yeah, yeah. I mean, this limit just goes to infinity, and what do we see? That just means like the limit doesn't exist, right? Yeah, and moreover, logically, you can say that it's not differentiable because it's discontinuous at that point. So, all in all, wherever something is just discontinuous, you don't have differentiability. Yeah, you don't need to check whether or not the limit is the same. You can just say that okay, it's not differentiable because it's discontinuous at that point, right? That's what I will do at least. Okay. Yeah, whatever. Continuous but not differentiable. Without it is part of it. Look, that's exactly what I'm saying. This cannot be differentiable, even if the limits are the same. It will never be differentiable because it's discontinuous in the first place, right? Okay. If a function is derivable, that is differentiable at x equal to a, it implies continuity. That must be the case. Otherwise, how can that happen? Right. If a function is continuous at x equal to a, then it does not imply differentiability. That makes sense. If a function, so look at this function, right? Definitely makes sense. Function y equal to f of x is not differentiable at x equal to a, then it does not imply discontinuity. Yes. Right. If a function is discontinuous and x equal to a, then it implies non-differentiability. Yes, that makes sense. Because in every single case of discontinuity, we saw that it's not differentiable. These two limits don't make any sense, right? Okay. Yeah, the same definition as what we had for continuity. That, yeah. Okay. Still, let's just do this thing. Fine, right? Huh. Oh, okay, wait. Fx is said to be differentiable over a closed interval if so f of a f dash of a plus and f dash of b minus, those exist finitely. Oh, so like even at the edges of your domain, you could still have differentiability because there is no definition for the left hand derivative. So what do we do? Just think about what the right hand derivative is, right? Is that continuous? If it is, then there you go. Right. So if this thing like the right hand derivative, if that exists and the at this point and the left hand derivative exists at this point, then it's actually, yeah, differentiable in this interval. At this particular point, I don't know. Can you say it's differentiable at this point? Uh, Wait, let's check the definitions once again. Well, they didn't say anything like that. I guess it's not differentiable at that point because it's not, yeah, the derivative is not defined for this. Okay, this is getting complicated, isn't it? How do you know? Okay, it depends on what the definition is. Okay, maybe we'll see something later. Okay. Or maybe we'll just never get these kind of questions. Who knows? All polynomial functions are, come on, I know that. Okay, comment on the differentiability of fx is equal to xx. Oh, that is an illustration. We don't want that. So yeah, now we know about differentiability, it seems. Because we can actually solve problems this way, even if we are not completely clear what's going on. Properties of differentiable and non, okay, we don't want that. We'll do it by ourselves if we want. Keep on going. All right, inch of axis. Let's do it. First question. Let f of x is equal f of x plus y is equal to f of x times f of y, and f of x is equal to 1 plus x g of x g of y, where what is this? Limit as x tends to 0 of g of x is a, and limit as x tends to 0 of capital G of x is b. Then f dash of x is equal to k f of x, where what? Where k is equal to, look, first of all, okay, is this function differentiable or not? Because then you can like take a derivative at every single x value, right? It is in fact. Wait. No, it's differentiable at x equal to 0. Okay, it's continuous at x equal to 0, right? Um, it didn't actually give us anything about what it is in general. So yeah, just assume it's continuous and differentiable, right? Just assume that everywhere. So then it's actually doable. So first of all, take a single derivative like f dash of x plus y. You know what? Let's take the derivative with respect to x only. So partial of the left hand side upon partial x. That will just be f dash of x plus y, right? That's equal to f dash of x times f of y. Okay, this might look new to you because it could be possible that you don't know what I'm doing. But I'm taking the partial with respect to x of the left hand side, right? Which is just f of x plus y. And that's equal to partial with respect to x of f of x times f of y. Now, what does this mean? That just means I'm changing x without changing y and then figuring out what's the derivative, right? As I change this, yeah, it's actually hard to tell you what's going on, right? So the left hand side is actually pretty easy. It's just the standard limit definition, right? You don't have to worry about anything. So it's just equal to f dash of x plus y, right? It's just the standard limit definition, nothing else. This thing though, you're only changing x, you're not changing y. So take y as a constant. This is like defined in this way: f of x plus h, f of y minus f of x, f of y upon h. Right. That's what this means. Okay. And the limit, of course, as h tends to 0 of this thing. So this is basically the same thing as f of y because you can take that out of the limit, and then you just have f dash of x, right? So you get this equation, and then similarly you will get something for this, like f dash of x plus y is equal to f of x times f dash of y, just taking partial with respect to y of this equation, right? Yeah. Now what we can do is just put y equal to 0 in this equation. So it just becomes f dash of x is equal to f of 0, which is 1 plus ap, right? Yeah. So wait, is this actually defined at x equal to 0? I don't know. But they're saying the limit exists at least. So I'm gonna assume that we can actually define it. We can remove any discontinuity that might be there. Then just do it like this. So it's 1 plus ab. and then f dash, right? So f dash of x. Oh, that's interesting. So all that means is like 1 is equal to 1 plus ab. Uh, wait, something doesn't make sense. Wait, what happened here? Huh? If f dash of x is equal to k times f of x. Wait, this should have worked. Can I put y equal to 0? This is not making sense. Well, it's saying that AB should be 0 unless the derivative is not defined. Oh, well, that's weird. But then, how do I do this thing? Wait. Okay. Think about it. Your f of 0 must be 1. So your A and B, okay. AB, that is automatic. Oh, that's x times. I should have seen that. It's x times of g of x and then capital G of x, right? Oh, that makes sense. Yeah, it actually does. So when you put 0 in there, it actually just becomes 1, right? So yeah, that should have happened, of course. So f of 0 is 1. We can say that. And now we can't put y equal to 0 in there, unfortunately. But let's try to do something else. Let's just say, let's put x equal to 0, right? So that will just mean f dash of y is equal to f of y times f dash of 0. So you just have to figure out what f dash is at 0, and then you get the value of k, right? Yeah. Wow, that's weird. Uh, Literally don't know what's happening. Come on, think about it. F dash of 0, we don't know what that value is. Huh. We'll have to do it the proper way. Just assume it's some kind of constant. Let's just say c. Then you have this thing, f dash is equal to f times c, which means that f is equal to it's of this form a, and then you got e power cx, right? Yeah, where a and c are constants. So I mean, c is already, you already know what c is, and then just put that in there. It is gonna work out. You can also do the usual differential equation thing, like natural log of f is equal to cx plus some kind of constant called k. I don't know. K is already used. Call it eta, whatever you want to call it. Then e power this thing. It's like f is equal to e power cx, and then e power this thing just a. So a cx. But then you can extend this to things that are not positives, like they might be negative, and you can just say, okay, maybe this is like a complex number. Who knows? So thinking of this thing as a complex number, it definitely makes sense, right? And yeah, that explains it. So the general solution for this differential equation, it's like f is equal to a e power cx, right? Okay, so yeah, that makes sense. Uh, okay, what was I doing once again? So f is equal to a e power cx, awesome, and of course your f dash that should be, sorry, okay, f at 0 that should be 1, which means that a should be 1. So f equal to e power cx. Yeah. And more like e power kx, because this should have been k actually. So f is equal to e power kx. That explains why this is happening. Okay. Well, yeah. Uh, what else? They didn't give us anything else. I mean, k could be anything, right? Okay, maybe not. They did give us what it is at 0, but then we don't care about that because it's going to be 0 in any case. Huh. It's a limit, right? Okay, that's interesting. How do you even use this in that case? Oh, I know. Just take a derivative of this, equation. That is like f dash of x is equal to, well, that's gonna be gone because of 1. And then you got g of x plus, um, rid of this time, which is like x g of x, and then you got g dash of x, and then plus x. The only problem is it could be possible like this thing is not defined, or this thing is not defined at x equals 0, and then something like that could happen. That's the problematic thing. Yeah. But in case it is defined, which is I think what we should assume, because this whole question rests on the assumption that everything is differentiable everywhere. Otherwise, there's no way of solving it. So if that is the case, then you can get rid of these guys, because at x equals 0, which is gone. So what does that mean? F dash of 0 equal to g of 0 times capital G of 0, which is just AB, right? So yeah, C should be the answer. This is very wrong. It just feels so wrong to do it like this, assuming differentiability. Fine, what can I even do? Next question. Second is that f be a function that is fine. Okay, once again, same kind of stuff. So this is the Cauchy equation, right? It's actually very well known. And the solution to this thing is fx is equal to kx under the condition that fx is continuous everywhere, right? Yeah, and we just assume continuity, right? We don't. Yeah. Okay, so fx is kx in that case, where k is a constant, and fx is equal to x cube phi of x. So like phi of x is basically fx upon x cube. That's what you're saying, right? Phi of x is equal to k upon x square. Okay, for all x and y, where phi is a continuous function. Well, this doesn't look so continuous. At x equal to 0, it's not continuous, unfortunately. F dash of x is equal to, it could be k. Hey, we know a way that this could be made continuous by assuming k equal to 0, right? Yeah. I mean, since they're not telling us what functions we're dealing with, why don't we assume f is equal to 0, right? F is a 0 function, then that just means like 0 equal to 0 plus 0, which makes perfect sense. And then phi would be 0, right? Yeah, just assume phi is the 0 function. Ah, of course. Assume phi is the 0 function. And then you get f and phi that satisfy this equation and all the conditions. There you go. Phi is a continuous function, and right, because if it's not, then how can you do this? Because it's like it's gonna go to infinity when x approaches 0. You can't make this continuous. The only way is k should be 0. That just means f dash is 0. Yeah. What's this g dash? Where's g? There's no g involved. What are you talking about? F of 0? What? It's just 0. Yeah, C is the answer. The only way this could be made continuous is if k should be 0. Next question. Third. Okay. Once again, the same as the last time. We already got a solution, just e power ax, where a is some kind of constant. And that's assuming continuity and everything that's necessary for this. But hey, okay. For all x and y. Okay. And f of x is good. Why did we go from that to this all of a sudden? F of x is equal to 1 plus x phi of x natural log of 2. So, okay. The limit is x tends to 0, phi of x is equal to 1, then f dash of x is equal to. Oh. So, as x tends to 0, your phi approaches 1. Okay. Which this means like this thing would be 1, right? We already know that. Okay. And, sorry. What were you doing? Wait, wait a second. This thing, it already has f of 0 equal to 1, right? This already says that. So that thing would not be there in any case. Because a and then here's a squared doesn't make sense, right? A must be 1. Okay. Now f x is equal to 1 plus x phi of x. Let's differentiate this thing. F dash of x is equal to what? Okay, wait a second. As x tends to 0, this, okay, we don't care about that because it's going to be 1 in any case. So just differentiate, and so what do you get? Uh, that's going to be 0 in any case, right? So just phi of 0 natural log of 2, that's f dash of 0, which is just a, right? And that's equal to what? That's equal to 1 times natural log of 2. So yeah, it's like e power natural log of 2x. That's what f is equal to. So basically like 2 power x, right? So f dash of x is just 2 power x natural log of 2. Yeah. So what is this natural log of 2 power? What? I mean this thing natural log of 2 power x. You could say so because this can be written like that. Sure. No, this is not correct. Log of fx square. It's like 2 natural log of fx. No, it's a, of course. Next question. Fourth. Fourth is if fx is equal to this thing. Once again, the same as last time. So we're going to assume a e power ax, right? And in this case, a will not be 0. Instead, so when you put x equal to 0, what do you get? Like, just get x equal to 0 and y equal to 0 as well. So a is just equal to 2a squared, which means either a could be 0. That is something that will work. But then this doesn't make any sense, and this doesn't make any sense. So a cannot be 0. That just means a has to be 1 upon 2. So yeah, like f is just 1 upon 2 e power ax. Cool. What you are saying is, right, f of x is this thing. Okay, we got this expression. Then f dash of 0 is 3. A upon 2 is 3. A is 6. So it's 1 upon 2 e power 6x. And f of 4 is 2. Something's not going correct. Dash of 0. That what is going wrong for all xy? Now it must be like this, right? Should be it's a multiplication over there. How can this even be? How can f of 4 be something like 2? It's supposed to be e power 24 upon 2. It doesn't make any sense. No, it doesn't. How can you have this? It's not making sense. A must be just 1.2, of course. Right? Yeah. Okay, I mean, this is supposed to be working, right? No, it's not making sense. How can you have a function like, okay, it should not be continuous in that case. Maybe that's gonna make it work. But this is for all xy, right? Okay, what do I do? Yeah, it doesn't make any sense. So none of these. Or maybe I should just say that no such function exists. Yeah, like just figure out a function that can have these properties. What function would do that? I couldn't figure it out. And most likely there's no such function. Okay. Fourth is in fifth. If f is differentiable function satisfying f of 0 is equal to 0 and g of x is equal to f of x upon x, okay, then value that should be assigned to g of 0 so that g is continuous at x equal to 0. Okay, so as x tends to 0, it's like the 0 upon 0 thing. Okay, that g is continuous at 0. It's a differentiable function. You are saying you can just take the derivative, right? Yeah, it's just equal to f dash of 0, of course. So your g as x tends to 0 is the same thing as f dash of 0 because L'Hospital's rule, that's what it is called, I think. So yeah, g should just be f dash of 0. Next question. Sixth. if f of x is equal to cosine inverse of 2x upon 1 plus x squared, then f is differentiable on, okay, cosine inverse of 2x upon 1 plus x squared. Fine. Then, oh, you know what? Just put x equal to tan theta. Then this just becomes cosine inverse of cosine of 2 theta, right? But then, okay, you might have something like negative and positive and whatnot. So for that, you will have to put, let's just say, okay, theta is in 0 to pi upon 2, right? So let's say x is equal to tan theta. Wait, what about the negative ones? We should also have the negative ones though. Yeah, that won't do it. No, it won't. It's like 2 times 1 plus tan square theta, just 2 theta, of course. But then the negative values should also be there. It's supposed to be cosine of 2 theta. Cosine of 2 theta can be negative as well. So we'll just say, okay, you know what? Let's just say theta, it goes from 0 to pi. No, something's not right about it. Because what will happen is, right, it's not just 2 theta, it's 2 theta in some interval and something else in some other interval. That doesn't make any sense, right? Ah, I don't like this. Fine. Then it's like cosine inverse of cosine of 2 theta. That's what is happening, right? So 2 theta goes from 0 to 2 pi. So in 0 to pi, it's good. It's just equal to 2 theta. So this is equal to 2 theta when theta is in 0 to pi upon 2. I should really do this thing, right? But otherwise, when it's not, it should be 2 theta minus, wait, no, 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 no. And it's, okay, 2 theta is something like pi plus something. Does that make sense? Uh, it's more than that, right? Mm-hmm. Like 2 pi minus, yeah, that makes sense. So our 2 theta value, this is more than pi now, right? So this thing is really the angle that you are looking for. So it's just 2 pi minus 2 theta that you look for, right? So that should be the thing, 2 pi minus 2 theta when theta belongs to pi upon 2 pi. All right, cool. So now, yeah, let's do the thing. So it is 2 tan inverse of x when x is positive, because at 0 it's just 0, and then at pi upon 2 goes to infinity. So whenever x is bigger than or equal to 0, it's this thing. And it is 2 pi minus 2 tan inverse of x when x is negative, right? So at x is equal to pi, it's going to be negative, and then at pi upon 2, it's, yeah, okay, that makes sense. So whenever x is less than or equal to 0, it's this thing. So at x equal to 0, this will just be what? And wait, theta is going from, it's not exactly tan inverse because, yeah, it's not tan inverse, unfortunately. It is just theta, in fact, because this range is not the range for tan inverse. So it's supposed to be this thing, it seems. It's getting just so complicated, isn't it? Yeah. Okay, then what do you have? So where is this differentiable? Okay. So this is the thing. This is our function. Yes. So f of x is this thing. And you can always figure out what theta should be given this and that, right? So what do you want? You just want f dash of x. That's like d by dx of well, this thing. So first of all, in this range, it's like d by dx of 2 theta, which is 2 d theta upon dx, which is like, okay, 2 upon dx upon d theta. Does that make sense? And then x is just this thing, it's 2 upon secant square of theta, which is like 2 cosine square theta. So that's what f dash of x will be in this range. And then, so it's this thing when x is cosine square of theta, when x is bigger than or equal to 0, and when right over here we just have like negative 2, and then you got d theta upon dx, which is 1 upon dx upon d theta, which, yeah, okay, just do that over there. So dx upon d theta is just secant square theta d theta, secant square theta once again. So it's just negative 2. Oh, it should be 2 over here as well. So negative 2 cosine square of theta when x is less than or equal to 0. Now that's good, isn't it? And now you can use the fact that cosine square theta, okay, that is like 1 upon secant square theta, and then secant square theta is just 1 plus x squared. So our f dash really is this thing. It's 2 upon 1 plus x squared when x is bigger than or equal to 0, and it's negative 2 upon 1 plus x squared when x is less than or equal to 0. Yeah, that's the thing. Okay, so what do you want to do with this function? Okay, that's what f dash of x actually. Right, then it's differentiable on. So as x approaches 0, yeah, it's a non-removable discontinuity. So except 0, everywhere else it's defined and it's good, and yeah, it's differentiable. So this looks good. B. Next question. Seventh is, let f of x be a differentiable function satisfying the condition. This condition is an even function. Okay, for all real x, the value of f dash of 0 is, oh, okay, that makes, so d by dx of this thing is equal to d by dx of this thing, right? Because LHS is equal to RHS. Yeah, so for all x, that's the main point. Because it's true for all x, you can just take the derivative on both sides. Which means negative f dash of negative x is equal to f dash of x. So like the derivative should be, whoa, that's weird. I was not expecting this to happen. Okay, whatever. Then the value of f dash of 0 is, so just put x equal to 0 in there, you get negative f dash of 0 equal to f dash of 0, so it's 0. A is the answer. Next question. Eighth. The function, this function, is like 1 upon u plus, what the hell? 6 u plus 2 and then u plus 1. Okay. Is, you know what? I want to split this up or something. Whatever. So where u is, what is this? Why? 1 upon x minus 1. Seriously. Okay, first of all, it's not defined as equal to 1. So it's continuous at that point because, oh god. Yeah, I mean, parts of it are not defined, right? Yeah. So I think at x equal to 1, it should be discontinuous because in reality, what we're actually doing is like 1 upon x minus 1 squared plus 1 upon x minus 1 minus 2. So when you will put x equal to 1 in there, the first thing you will encounter is 1 upon 0, which is not defined. So you just give up at that point, right? So think of it like you're putting this definition into a computer. What would it give you? It will give you not defined x equal to 1. Even if this was somehow definable, it will give you 0, right? So I think that's what we should be doing. So yeah, x equal to 1, that is a point of discontinuity. Otherwise, what points do you have where it's discontinuous? One point would be whenever u is equal to negative 2, and other would be when u equal to 1, which would mean 1 upon x minus 1 is equal to negative 2, and 1 upon x minus 1 equal to 1, which is like x minus 1 is equal to negative 1 upon 2, so x equal to 3 upon 2. Wait, no, 1 minus, okay, 1 upon 2, right? And this is like x equal to 2, right? Yeah, should be the thing. So this point, it's discontinuous. At this point, it's also discontinuous, and x equal to 1 is also a point of discontinuity. So yeah, it should be this way. B. B is the thing. Next question. Ninth. Ninth is the graph of the function y equal to x has a unique tangent at the point a comma 0 through which the graph passes. Then the limit, this limit is at what point? Okay, at this point it has a tangent through which the graph passes. I mean, okay, the tangent is to the graph, right? Or something. Oh, so the graph passes through this point. That's what you're saying. Okay, fine. Ah, you should have told me. So you are saying like f of a equal to 0 and f dash of a is defined. Huh. Then limit as x tends to a of, what is this? Natural log of 1 plus 6 fx. Is this a fractional part or is this bracket? Does that, I don't know. Uh, okay. Wow. No, it must be just a bracket. It should not be a fractional part, because if that is the case, if it's actually the fractional part of 1 plus 6 f of x, this would just be the same as 6f, right? Because f approaches 0. So then natural log of something that's 0, that's going to be infinity. And then divide by 0, that's not good. So this must be just a bracket, which means this thing can be approximated as 6f, and this is like just 3f. Because yeah, like f is becoming 0 from both sides, right? Yeah, then even if it's like negative or positive, it doesn't matter. It doesn't matter because you can approximate this in both cases. And then it would just be 2, right? This limit is 2 in both cases. The left hand limit and the right hand limit, both. So there we go, that's this thing. Next question. 10th. 10th is exhaustive set of points where f of x equal to x mod of x is differentiable is. Okay, so for positive x is just x square, negative x is negative x square. So it's like 2x is the derivative for positive x, and it's negative 2x at negative x values. So at x equal to 0, it's 0, right? That's the derivative. It's also continuous because mod x is a continuous function, x is a continuous function, so the multiplication of any operation, in fact, except division, of course, that's continuous, right? Yeah, that explains it. So that means throughout the real number line, it is in fact differentiable. Yeah, so D is the thing. Next question. Um, okay, fine. Where is it differentiable? Okay, so it's like mod x less than 1. What? God, I don't like this. Okay, let's just split this into sections. First, you have, this is like negative 1, this thing is 1, and this thing is, right. Uh, yeah, so whenever mod x is less than negative, less than 1, that just means you are in this range. So it is what? Tan inverse of x, right? Yeah. Uh, so it's continuous I mean, sure, it is continuous because tan inverse is a continuous function. At x is equal to 1 and negative 1, this will just be pi upon 4 and negative pi upon 4. And oh, okay, that already does it. You know, it's just discontinuous at these 2 points. So we don't actually have to look any further. And this is continuous differentiable in its, range, but then at the boundary, not so good because it's discontinuous. So what does that mean? Yeah, it's differentiable at all points except at x equal to 1 and minus 1. Yeah. Okay, at 0 is this, so at 0 is will be tan inverse of x. It's like 1 upon 1 plus x squared. No, it is differentiable at 0 as well. So just C is the answer. Next question, 12th. Uh, fx is equal to x, and then you got, what is this thing? X power 2n plus 1, mod of that. Huh, interesting. Well, you can always write like this thing, x, and then you got power 2n and then mod of x, right? Pretty much what we saw the last time, right? Something like this, x mod of x. But then this is x power 2n. Okay, whatever. So this is a continuous but not differentiable at x equal to 0. Who told you? It depends on the n value. If n is, oh, it's a natural number, then yeah, it's already just differentiable, continuous, whatever you want to call it. Yes. So it is continuous, sure, and it's also differentiable. I can just say that because you know, x power 2 n plus 1 when x is greater than 0, it's negative x power 2 n plus 1 when x is less than 0, but the derivative, it's still 0 at x equal to 0 from both sides. So yeah. 13th. 13th is f of x is equal to x or minus x if x is rational. And oh my, that is not good. Oh, it's discontinuous at every single point, it seems. Because between two rational numbers, you can always find another irrational number. Yeah. So yeah, it's discontinuous everywhere. We don't even, okay, I think we should not do it like that. At x equal to 1 upon 2, you are saying. So that's the point when both of these in fact are the same value. It's at least continuous. Yeah. Okay, it's getting complicated. Wow, I never thought this would be like this. It's continuous at x equal to 1 upon, I don't know. Doesn't look like that though. But the limit definition works because, so exactly at x equal to 1 upon 2, our function's value is 1 upon 2, right? And when you take the limit, well, it's, yeah, like the limit is 1 upon 2 from both sides, although slopes are different for different points that you take the limit on. Ah, so you can say that, sure, it is probably continuous using the definition, but then it doesn't look so continuous, does it? Fine, so it's continuous but non-differentiable. This is weird. If f of x is equal to, what is this? Okay. Oh, okay, fine. Then it's continuous but not differentiable. X equal to 1. Oof, this is weird. So at x equal to 1, right? So when x is equal to 1 plus h, what is the thing? So h is just some number that's approaching 0 plus, right? Then at that point, this f thing just becomes h. You just want the floor function. It's just 1 plus the square root of fractional part is just h. Yes, yes, that looks good. So it's this thing when, yeah, and then the limit. So is this continuous? It looks like it was, it's 1. So the right hand limit is 1. The left hand limit, okay, on the left hand side, this is gonna go to what? 0, and this will be going to square root of approaching 1. So 1, right? So yeah, left hand limit and right hand limit actually are the same, and exactly x equal to 1, of course, just have 1 plus square root of 0. So yeah, 1. That looks good. So it is in fact continuous. Is this differentiable? You'll have to see that. So when it's 1 plus h, where h is in the range 0 to 1, then you can write like this. Okay, then the derivative of this thing would just be 1 upon 2 square root of h. And then when it's like this, x is equal to h, right? What am I doing? Just put x in, of course, like x will be a fraction by itself. So then this is just 0 plus square root of x. It's like, okay, 1 upon 2 square root of x. So this derivative as x approaches 1, it just becomes 1 upon 2, and this derivative becomes non-existent because as x approaches 1 from the right hand side, h approaches 0. So this is like 1 upon 0. Yeah, it's infinity basically. So it's not differentiable, although it is continuous. Okay, yeah, that looks good. A is the answer. Next question, 15th. 15th is let f and g be differentiable functions satisfying g dash of a equal to 2, g of a equal to b, and f of g of x is equal to identity function. Then f dash of b is equal to, so g dash of a equal to 2. Okay. Oh, both are in fact differentiable. That's awesome. G of a is equal to b. F of g of x is equal to I. Sorry, equal to the identity function. So basically, what you're saying, f of g of x is equal to x, right? Yeah. So f of g is equal to x. Okay. Then f dash of b. Sorry. Just differentiate this first of all. Just get f dash of g, and then you got g dash is equal to 1. So when you put x is equal to a in there, you'll just get this thing f dash of g of a, which is just a b, and then you got g dash of a, which is 2. So that's equal to 1, which means f dash of b is equal to 1 upon 2. Looks good. Next question. 16th. If f is equal to this sum from x equal to 0 to infinity of x power n upon, have I seen that? Yes, it's just e power. Okay, that is not something I've seen. Natural log of a to the power of n. It's like this thing, x natural log of a, that to the power of n upon n factorial, right? That's the general term. Summation of this thing from 0 to infinity, that just e power x natural log of a, because like this thing, yeah, this is just a Taylor series for e power x. I mean, okay, if this was not x on x natural of a, but just x, this would be the Taylor series. So it's just e power x natural of a, which means a power x. That's what this function is, right? That's what f is. Okay. Then, and of course, a should be some kind of positive number. Okay, that's obvious because x will be all kind of real numbers. That must be the thing. Then at x equal to 0, f will be 1. Oh, okay. You mean its properties. Fine. Is this differentiable? Yes, it is. Is this yes, it is. That was easy. Okay. Yeah, it is differentiable. So B is the answer. And it's also continuous. Next question. 17th. Fx is this thing, x plus x upon. Isn't that like a GP though? Just take x common. You got this thing 1 plus 1 upon x. Yeah, whatever. You get the thing. Uh, um, yeah, like 1 upon 1 plus x. So x is what? This is like positive, negative. What's going on? So when x is bigger than 0, like this series just becomes like x, and then you got 1 upon 1 minus 1 upon 1 plus x, right? It becomes this thing when x is bigger than 0, which is just x upon, like, what's this thing? X and then upon 1 plus x. So that cancels. So when x is bigger than 0, it's this thing. But then when x is less than 0, this thing, take that x out, sure. But now look at this series, 1 plus 1 upon, yeah, okay. It's like 1 plus 1 upon 1 plus x. Oh god, this is not good. So at x equal to 0, it has the right hand limit, right? It's approaching 2. But the left hand limit doesn't make any sense, right? Yeah. It's not a closed form anymore, unfortunately, and you can't just do it like you would usually do. Uh, something else, something else. Maybe try to convert this to some kind of. No, that is not good. Don't do that. It won't help at all. Take an x out. X is approaching 0. Oh, okay, that could be used, I guess. Hey, I could say it's like 1 upon 1 plus x, and then plus 1 upon 1 upon x plus. So, like 1 upon x is just n. Okay, let's just say negative n, and n is tending to infinity. Does that make sense? Yeah, because that would just basically mean that x is approaching 0 minus. So this is like 1 upon n plus 1 upon n plus, what is this thing? Okay, you know what? Like, okay, the first x will not think about it in any way because it's approaching zero in any case, right? So just forget about this thing. It's this thing. 1 upon n plus 1 upon, so that's not supposed to be there. 1 upon n plus 1. Okay. Wow, that's making sense now. Because, yeah, okay. So just put negative. Uh, let's just say it's negative and negative 1, right? The same thing, right? So it's just negative n, okay, 1 upon negative n plus 1 upon negative n squared and so wait, no, that's the problem. But negative 1 upon n is actually approaching 0, right? You could use that. Sure, you could use that. That makes a lot of sense actually. Wait, okay, no, don't do. Oh, now I get what's going wrong because I was thinking it's x power, whatever this exponent is. It's not the thing. It's just 1 upon this. Yeah, it won't work. It won't work. Think about it. Okay, all we have to do to show that this is not going to work is show that actually one of these uh, things, like it goes to something that's not good, right? And then you're good to go. Yes, you can do that. Hey, you can always do it by adding a limit and think of it as a GP first of all. So we have this thing x upon, okay, that's falling into that category. So switching limit and sum, when can you do that, right? It's falling into that kind of category. Okay, so it's like this is the sum. Okay, so limit as n tends to infinity of the sum of so like take that x common. The inside stuff is this thing 1 upon 1 plus x to the power of n. Oh, what am I doing? This x, then this limit as n tends to infinity. Then you got n equal to 0. Start off from that till n equal to capital N, right? Yeah. And then you are saying the limit of that thing as x tends to 0, right? I guess that's the thing. Okay, it should be 0 minus. Okay, this is actually what we should be doing. So first of all, this limit, what's that going to be? It's just a GP, right? Infinite GP, guess what? It's a GP in the end. So first of all, we'll just do this thing and then we'll figure out the limit. So it should be this thing 1 minus. It's kind of complicated actually. What do I do? What do I do? 1 minus r, which is 1 upon 1 plus x, like 1 plus x power negative n. Oh, sorry, just negative 1. And that to the power of what? Capital N, right? Or n plus 1 or whatever, just whatever you want. Capital N, negative of that, upon 1 minus 1 plus x power negative 1. That should be thing. So this is like 1 plus x power capital N minus 1 upon, so that's just 1 plus x power n going over there. It's this thing 1 plus x power n minus, you know what, just take one of these guys on. Okay, yeah, 1 plus x power n minus 1, and then take one of these guys inside, so it's just 1 plus x and then you got minus 1, so it's just this thing. Okay, and then some x. So the limit as n tends to infinity of this thing, right? That's very unexpected. So since x is actually a number that's negative, right? Well, this thing is actually gonna go to 0. So just negative 1 upon, hey, you know what? Okay, that's also going to 0, right? So that's just negative 1 upon, that is something negative. We don't care about what that is. And this is going to 0 as well. So yeah, like that's the thing. It's not defined. I have proved that this doesn't make any sense. I mean, yeah. So this is discontinuous at that point because, right. So B is the answer. I mean, it would be wrong to say it's not defined. More like it doesn't work nicely. It actually is an asymptotic thing going on, right? Okay, as x tends to, come on, why is this so weird? The problem is that you will have to do the inside sum first and then the outside sum. If you could not, if you could do it the opposite way, okay, that would be really wrong, because then all integrals are zero in that case, right? So that's not what you should be doing. Uh, this is so weird. Something that's infinite everywhere, how do you graph that? You can't graph that, right? So there's no way to actually figure out what the limit should be other than using the formality, right? Yeah, formal definition would say it's actually infinite, right? It doesn't matter what's going on, it's infinite. So yeah, formally we don't know what it is. But hey, next question. So formally we know what it is, but like, the problem is like we don't know how is n related to x. If there was some kind of relation, you could have done it. But because they are independent, the thing doesn't make any sense. Yeah, it depends on the relative sizes of capital N and X, right? And when it says infinite, it actually means infinity. So we can assume that this infinity, like this infinity, is actually much bigger than one upon x kind of infinity, okay, mod of one upon x kind of infinity. Then that would mean, yeah, this is actually going to be infinite. Sure. Next, the function, this function, okay, is 1 minus 2 is, okay, I see what's going on. It's the derivative of this function, right? D by dx of 1 minus, not 1, 3, x minus x squared. You know what? Let's do it like this thing. 1 plus x minus x squared plus x cubed and whatever. Just keep on going. Right. It's right of this thing, which is like the derivative of, well, this is usually used for what? Natural log of, oh, it should have been, wait, let's just say negative. Yeah, that's gonna work out. It's negative over there. So it's a negative, and then you got natural log of 1 plus x. Cool. So it's like negative 1 upon 1 plus x. That's what this. Wait, what? Sorry, what am I doing? It's not natural log. Okay, negative 1 upon. Yeah, that's the thing. Negative 1 upon 1 plus x. That's what it is. So the derivative of this thing would just be this. Yeah. Right. This is what it's going to be uh, when your x is between negative 1 and 1. Okay. So when x is not equal to negative 1, it's just approaching negative 1, right? It's kind of complicated actually. So when x is bigger than negative 1, you just get this thing, right? It's approaching infinity or whatever. Oh, okay, it's already just discontinuous. You don't have to do anything. So it's discontinuous, which is B, I think, because this thing already, I mean, yeah, just look at this thing. When you put x is equal to negative 1, it just goes to infinity, right? So you can't do that. Uh, and when you have x less than negative 1, then what does this go to? This doesn't converge in the first place. So yeah, yeah, right. That makes a lot of sense. Sure. That's done. Next, 19th. Let f be equal to a. What is this thing? Floor function of x plus p e power. God, okay. If f is differentiable at x equal to 0, then, oh, okay, fine. So the usual thing, first we just say when x is bigger than 0, this becomes what? It just becomes, well, okay, this is gone. You got b e power mod of x, which is b e power x, then plus cx square, basically. That thing is x square in both cases. This is the thing when x is bigger than 0 and when it's less than 0, and of course in the certain range that we are talking about. So that would just be this thing, negative a plus b e power negative x. So okay, so yeah, e power negative x. Yes, and this would still be just cx squared, right? So the derivative of this guy. Well, first of all, check if it's continuous or not. So at x equal to 0, this will just become b, and this will become b minus a. Yeah, yeah, right. It's discontinuous. So already, what you mean by it's differential? It's not. You can see that it's not. First of all, it's not continuous. How can you even say these are like this is? Oh, unless your a was 0, so a must be 0. Okay, if that is the case, then yeah, you get this thing. Next, it should be differentiable. Well, this is the same stuff. Um, yeah, b e power x negative b e power x in the derivative. So b and negative b must be the same, which means b must be 0. So b is also 0. And C can be anything. So C belongs to real because polynomial terms are good. They are infinitely differentiable and always continuous. So there we go. A equal to 0, B equal to 0, C belongs to real numbers. Next question. Actually, it's not even that it belongs to real numbers. It could be complex numbers as well, but then like C can be anything. That's what it's saying basically. Next. If 4x plus 3 mod of y equal to 5y, then y as a function of x is 3 mod of y equal to 5y. Oh, okay. So when y is bigger than 0, then you just get this equation 4x plus 3y equal to 5y. So 2y equal to 4x. So y is just 2x. And when y is less than 0, um, this will just be like 4x minus 3y equal to, right? So y is equal to 8y. So y equal to 1 upon 2x, right? Of course. So, oh, that's like y is a function of x. That's not what, it's not what's happening though. Huh. What I did is x is a function of y. Okay. So here's the y-axis and here's the x-axis. So when y is positive in this region, x is equal to y upon 2, right? Yeah. So something like this. And in this region, this is happening. So you got x as a function of y. The good thing is it's actually bijection. So yeah. Wait. Uh-oh. Something's not good. Oh, it should have been negative. Okay, that explains it. So it should be like this thing. It's 1 upon 2x, right? Okay. The slope should be like what this thing is. Yeah, that's the slope. That's the slope like this. Okay, yeah, that's it. So this is this line and that's this line. So yeah, it works. And as you can see, x is a function of y is actually a bijection, which means we can also write y as a function of x, which yes, like y equal to 2x, which happens when x is bigger than 0, and this happens when x is less than 0. That makes sense. Okay. So y is a function of x uh, is differential x to 0? No, it's not. Continuous? Yes, it is. So B is the thing. What is this dy upon dx equal to 2 for all x? No. It's only 2 for positive x. Okay, that does it, I guess. So 20 is done. Let's check the answers. So first C, second C, third A, fourth B. I don't know what this thing is. Fifth D, sixth C. Okay, seventh A, eighth B, ninth C, 10th D, 11th C. This thing is B, then A, then A once again, then C, then D, then B, then B, and then C, and then B. Okay, so sixth. If f of x is equal to this thing, then f is differentiable on. Wait, okay, that's not. So sixth, B is wrong, and instead it should be C. So you're saying at -1, it's what? What is this? Uh, Wait. So at 0, you are saying it's actually differentiable. Huh. But how can that be? At 0, it's not continuous. How can you even say something like this? This is just wrong, right? It's just plain wrong. You can see that at x equal to 0, so just, yeah, x is very close to 0. It's slightly more than 0. Then cosine inverse of something that's approaching 0 plus, right? Wait, okay, it is in fact the thing. Huh. Hey, that's weird. So that's like pi upon 2. And this is negative. Wait, okay, no, not negative. This is pi upon 2 plus something, right? Is that correct? Okay, so this is actually continuous at x equal to 0. That was unexpected. Uh, Wait, how did I get... something's not right about this thing. What about x equal to 1? It's continuous or not? Just 2 upon 1. Oh, it's like 1 is when it becomes equal to 1. So that's the cosine of 1, right? Which is just 0. And when it's more than that, it's like, okay, 1 plus x squared is always going to be greater than 2x. So you can actually, yeah, right. You don't have to worry about all of that. And of course, your equality will happen when x equal to 1. So when it's not 1, it's actually less than that. Wait, yes, it's less than 1, right? So just ahead of 1, it's less than 1 and something, it's positive, and okay, it's obviously doable at that point. Okay, that's not a problem. If there's no problem like that, then how is it that, it's getting complicated. So is this like really, wait, what was the thing? Sixth, right? So you're saying C is correct, that it's differentiable on this range, which means it's not differentiable at -1 and 1, right? Huh, interesting. So it's continuous everywhere, sure. Is this differentiable at 1 and -1? And what about 0? Is this differentiable at 0 or not? Um, okay, let's do this thing. X is equal to tan theta, where theta is just something that's bigger than 0, okay? And it's actually very small. So theta is bigger than 0, but it's actually approximately equal to 0, right? Then this thing just becomes what? Cosine inverse of cosine of 2 theta, just like it's 2 theta, right? Yeah, I mean, uh-oh, okay. Ah, shit. If this was 1 minus x squared upon 1 plus x squared, that would be cosine of 2 theta. Actually, this is a sine of 2 theta inside. So, well, that was bad. Really bad. This is actually like cosine inverse of cosine of pi upon 2 minus 2 theta. Okay, so everything that I did was wrong in some way. Hmm. Sixth was really bad. I didn't actually see it. Seriously, how could I have made such a mistake? Okay, fine. So, sixth, yeah, it's wrong. Isn't there like some other way to do it directly or something? Does our formula work all the time for the derivative of cosine inverse? Maybe it does, maybe it doesn't. We proved the formula only for, right, inverse square root, right? Inverse square root, that's a problem. Because sometimes it might be negative and sometimes not. And yeah, it's just really weird. Okay, so then what do I do? Uh, what about I just put x equal to secant theta, that's like 2 secant theta upon secant square. So just, nah, won't work. Just won't work. Sorry, two. Just put x equal to tan. We already did that. We already tried to put x equal to tan theta. And secant theta is definitely not going to work because 1 plus secant doesn't make any sense. It should be tan theta, and then you did everything, and then I don't want to do it once again. So fine, we just accept that maybe C is correct and B is wrong. Right. Other than that, what do you have? Fourth. So they're saying B is the thing. So f dash of 4 is equal to 12. Again, I don't know what function satisfies all these conditions at once, right? So what function are they even talking about? The only way a function like this would work is if you had something like 1 upon 2 and then a power x, right? So 1 upon 2 a power x, that's our function, then it would work for this equation, right? And then you're saying f of 4 equal to 2. Okay, first of all, f dash of 0 equal to 3. Um, that just means like natural log of, okay, maybe we should write like this thing, e power ax. What that means is like a upon 2 equal to 3. So a should be a 6, right? Which means it's like 1 upon 2 e power 6x. But then this condition doesn't make any sense because e power 24 upon 2, that's not 2 for sure. So how did this happen? That this satisfies this equation as well as these equations. No, it doesn't make any sense. You cannot find a function like that, right? That's the thing. You cannot find a function like that. So yeah, none of these is the answer, and B is not. This is wrong. Okay, I think we should stop here. How many more exercises are left? So there's in chapter exercise. Come on. Where's the next exercise? Oh, really? How long do I have to scroll down? So, right, you will have third exercise, which contains 20 more questions, and then you will have exercise 1A. Fine. So, I think we should stop here because there's a lot of theory after this as well, it seems. We'll have to read that first. Fine. So, I'll see you in the next video.